Hey everyone, I'm here today to talk about document layout analysis, which is a topic I know that a lot of you have been excited to see that relates to your final projects. So I'm really glad that we've gotten to this application now. And so this lecture is going to focus on document layout applications. And so suppose you have document images and you'd like to convert those into structured data that can power your downstream analyses. The first thing you need to be able to do in order to complete that task is to be able to recognize the layouts, because in kind of the quantitative data that we would typically work with, documents oftentimes have complex layouts. You know, it's not a single column book where you just need to know if you should read from left to right or top to bottom or right to left. Oftentimes we have tables or some other form of semi-structured layout, and in order to be able to convert this into data that we can analyze, we need to understand those layouts. Understanding layouts is also a prerequisite for OCR, which, as we'll see next class, almost always requires single lines as inputs. So even if you're using kind of an off-the-shelf commercial OCR engine, first of all, it's doing some type of document layout analysis to get lines. Okay. And so we're going to talk, broadly about different classes of computer vision problems in this space. And so the first type of problem is semantic segmentation. And so you see there that you are segmenting the image at the pixel level into different classes. So grass, cat, tree, sky. The second type of problem is localization, where you're localizing a single object within an image and classifying what that object is. The third type of problem is object detection, which is kind of like localization, but with an arbitrary number of objects in the image. And so you can see in this example, there's 2 dogs and a cat, and you've localized a box for where each of those dogs are located and the cat, and you've classified what they are. And then the final thing is instance segmentation, where in this case, kind of you're localizing each of the, you're segmenting each of the objects that appear in the image, and you have an arbitrary number of objects that can appear. All right, so as with other computer vision tasks that we've seen in the course, deep learning has transformed object detection and related computer vision problems. Okay. So I'm going to start out by discussing these problems that I just showed you. So semantic segmentation, classification and localization, object detection, and briefly instance segmentation. And so the main task that's of interest to us when working with documents is typically object detection. But these other tasks, and in particular localization, is a building block for understanding how to do object detection. All right. Sorry about that. Okay, so semantic segmentation. Our goal with segmentation is to classify all pixels that appear in an image. And we typically use fully convolutional models to do this, where we downsample and then upsample. And the upsampling is learnable. And so this differs from instance segmentation, where we're detecting individual objects and generating a mask for them. And instance segmentation is going to have a pipeline that's very similar to object detection. Okay, so semantic segmentation is kind of one of the older problems in the computer vision literature. And initially, what people did was to take a sliding window approach to treat semantic segmentation as a classification problem. And this is super, super costly because you have to run each of the patches through a ConvNet classifier. And so this was something that people did kind of before deep methods were used for computer vision, but it doesn't really make sense in the context of deep methods. And so the big breakthrough here was to realize that you could stack a reverse CNN with a regular CNN, so like a ResNet. And the regular CNN extracts the semantically strong features, and then the CNN in reverse scales this back up to the higher resolution to predict the mask or the pixel by pixel classification. Okay, and so if you'll recall from when we talked about convnets, you can think of regular convolution as this sliding window where we're applying filters across the image. And so in this case, we have a 3x3 convolution with stride of 2 and a pad of 1. So the filter moves 2 pixels in the output for every 1 pixel in the output. And the stride gives the ratio between movement in the input and movement in the output. So what is transpose convolution? And so this is giving an example of a 3x3 transpose convolution with a stride of 2 and a pad of 1. And so you see here that the filter moves 2 pixels in the output for every 1 pixel that moves in the input. And in this case, the stride gives the ratio between the movement in the output and the movement in the input. So when the filters overlap in the output, you're summing up from the input. And so I think that this example helps to make this clear, right? And so the output contains copies of the filter weighted by the input and summing where there's overlaps. This is often called fractionally strided convolution or deconvolution in the literature, but it is important to note that deconvolution means something different in signal processing. And so if you're familiar with the signal processing literature, that terminology might be confusing, and I think it's caused some confusion in the literature. All right, so that's semantic segmentation. And so I want to move on to talking about localization. And so in a localization problem, we know that there's only 1 object per image, which we want to classify and determine its bounding box coordinates. And this problem doesn't seem that likely to arise for us in practice because typically there's many different objects within a document image, but it forms a foundation for how we approach more realistic problems. And this is going to draw heavily on the machinery we already developed for classification, but it's going to add a fully connected layer at the end to predict object bounding box coordinates. And so in machine learning, 2 common problems are classification problems, which have a discrete output, and regression problems which have a continuous output. And regression is used in the same sense that we use it in economics. So there's a Euclidean loss. Sometimes people would use other regression losses for continuous outputs like L1 or smooth L1, but it's essentially analogous. Okay, so recall that our desired outputs from localization are a class. So this is a picture of a cow or a car or a plane, etc., and location. So the coordinates of the single object that appears in the image. The first is an image classification problem that we already know how to solve. The second is a regression problem, predicting 4 continuous numbers. And so recall that we can think of neural networks as Legos, and we can just add a regression head to the end of the CNN features extractor that is used for classification, and the network now has 2 branches with fully connected layers for classification and for regression. And the classification head will have a fully connected weights that predict the in-class probabilities from the features maps, and the regression head will predict 4 coordinates for that objects. Regression classification heads can be added after a fully connected layer or just after the last convolutional layer. And so to train this, we combine the 2 loss functions into a multitask loss, where there's a classification loss where we're taking a softmax and a regression loss. So we have a hyperparameter that tells us how to weight the sum of these 2 losses and changes the value of the loss, so we can't evaluate this hyperparameter using the value of the loss. Okay, so that's localization, and now I want to move on to object detection, which is plausibly the more practical problem. And so can we approach object detection as localization? Well, the problem is that our regression head outputs a fixed number, but how many coordinates we need to predict depends on how many objects are in the image, and that's unknown ex ante. Right? So it's not going to work because we have fixed size outputs and we have a variable number of objects in the image. So one approach would be to apply a CNN to many different crops of the same image using a brute force sliding window and classify each crop as object class or background and then treat it as a localization problem. And that's not going to work with a deep CNN because you need to apply a CNN to a huge number of locations, aspect ratios, and scales. Which is just completely unrealistic computationally. And so what people did initially when thinking about this was to use traditional image processing tools. So these are not deep learning. These are older tools to propose, for example, 2,000 regions where objects might be present in an image. And essentially it's looking for blobs of things. And this is kind of fast to run. Okay. And so this is what's called a region CNN. And so you have, this method to look for potential objects, and then you put those through a CNN, and you predict a category, adding a background class, and you also have a regression head to predict the correction to the bounding box, because the proposals from this method, right, aren't going to perfectly correspond to objects that you want to identify. And the backbone, we typically use a CNN. We're going to talk about transformer-based object detection later in the lecture. We remove the classification layers from the CNN, so it's just used as a features extractor, and this makes the network fully convolutional, which means it can take any input size, which is very important in detection problems, because you don't want to have like a code base that forces you to always resize your image to the same size. Because so you might need high resolution images. Okay, so what are the problems with region CNN? It's slow to train. It takes a lot of disk space because it's saving those region proposals to disk. The training is ad hoc, and inference is really slow. Okay, so like 47 seconds per image because you're making thousands of forward passage through the CNN for each region proposal. This is a 2014 paper. I will say this is like really, 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 really slow. Okay, compared to anything you might kind of want to scale. It's insanely slow. So we'll see the OCR methods we've been working on next class, where we're processing, literally many hundreds of millions of lines, and taking 47 seconds per image is just prohibitive for scaling any application. So the solution to this challenge was an architecture called fast RCN. It's supposed to be a fast version. And rather than running every potential region proposal separately through the COMNet, they reuse the convolutional features map, which is what's expensive to compute because you're passing it through this deep neural model across the entire image. And so essentially you take the region proposals that, again, you found through using this kind of older method, and you map those across to the features map that's been created from the convolutional neural network. All right. And so you need fixed size features maps to classify proposal regions into a fixed number of classes because of those fully connected layers. And so just crop the convolutional features map using each proposal and then resize each crop to a fixed size. So like 14 by 14 by com depth, using interpolation, usually using a bilinear interpolation. And then after cropping, you can do max pooling to get a final features map for each proposal. And so this is just illustrating this. And so we have this image, and there's some kind of blobby object that corresponds to a proposal for the bicycle, and we can find that in the output from the COMNet, and then we need to resize it because we're going to need it to be a fixed size in order to be able to take it to the classification head. Okay. So after extracting the convolutional features for each proposal, region-based CNN mimic the final stages of classification CNNs, where a fully connected layer is used to output a score for each possible object class. So in ImageNet, there would be like 1,000 possible classes. And we have these two objectives. We want to classify proposals into one of the predefined number of classes plus a background class for removing the bad object proposals. And so we just use a fully connected layer with n+1 units. And then we need to adjust the bounding box for the proposal according to the predicted class and use a fully connected layer with 4n units. And so essentially we turn this into a localization problem on each region proposal, but in an efficient way that's kind of reusing the CNN instead of passing each proposal separately through the CNN, which is very costly. So proposals above some intersection over union threshold with any ground truth box get assigned to the ground truth, and those, when we're doing training, and those below a threshold get assigned to the background. And targets for the bounding box regression are calculated as the offset between the proposal and its corresponding ground truth box, only for those proposals that have been assigned a class based on the threshold. And we randomly sample a balanced mini batch of proposals and use a multitask loss, which is the weighted sum of classification and bounding box loss. And for the bounding boxes, we only take into account the loss for the correct class. All right. So with this sort of method, you're going to get overlap between predictions. And so we use something called non-maximum suppression, which takes the lists of proposals sorted by score and iterates over the sorted list, discarding those proposals that have an IOU larger than some predefined threshold with a proposal that has a higher score. And you have to be very careful, like with this threshold. If it's too low, you'll fail to detect objects altogether, and if it's too high, you'll end up with too many proposals for the same object. And so I do think that, like, actually with NMS, like working with documents makes our life more straightforward, because if you're working with a image of a text document, by and large, you're not going to have different objects overlapping, right? Because if you put two pieces of text on top of each other, it's not going to be legible. Whereas with a natural image, there might be, like a cat, holding a ball or something, and those are both objects you're interested in, and they can totally overlap. And so I think you tend to want to be pretty conservative with NMS for document applications, because we really don't expect, there's obviously small amounts of noise, and so it's not like you would want to throw out every proposal that overlaps, but if there's too much overlap, it's very likely to be duplicate proposals for the same object, because you can't have text overlap and have it be legible. And so our final list of objects, we also can set a score threshold. So how do we evaluate object detection? We do that using a metric called mean average precision. And mean average precision penalizes you when you miss a box that you should have detected, as well as when you detect something that does not exist or detect the same thing multiple times. So in many papers in this literature, you'll see MAP that is in the 0.5 range, and people argue that this is good. But in our experience with documents, you usually need something that's 0.8 or higher. I mean, obviously your mileage can vary with the specifics of what you're looking at. But if you're trying to recognize a dog and you chop off a little bit of its tail, it doesn't really matter probably for your downstream purposes. Whereas if you're trying to recognize, say, cells in a table, and you chop off the 1 at the beginning of the number, or you chop off the 0 at the end of the number, that's going to matter a lot for your downstream statistical analyses with the digitized version of that table. So in general, I think in documents, we have a very high demand for accuracy. Okay, so what is mean average precision? So despite the name, average precision is not the average of precision, where precision is just your true positives over the total positives that you detect, which would be your true plus your false positives. So suppose MAP was the average of precision, that's obviously going to be problematic, because then recall doesn't enter at all, right? And so in this example, this is object detection. Application of object detection is self-driving cars. You fail to miss that guy that's about to walk in front of the car, and that's obviously a problem. We need to take into account both the precision and the recall of the method. Another thing that we need to note is so intersection over union is just the intersection between two proposals. So say your predicted proposal and the ground truth over the union of them. And we need to evaluate mean average precision at a certain intersection over union, right? Because you have to determine how much your proposal needs to overlap with the ground truth in order to count as correct. And so if the intersection over union threshold is 0.5 and the intersection over union value for a prediction is 0.7, then we classify that prediction as a true positive. On the other hand, if it was 0.3 and our threshold is 0.5, we would classify it as a false positive. Okay, so how well you find true positives is going to depend not just on your precision, but also on your recall, which is true positives over all the positives, which are your true positives plus your false negatives. And so suppose we have a data set that has 5 apples and there is 10 predictions for it. And so we kind of sort them in order of their probability. And as we go through them, by definition, our recall is going to increase as we say we have, more and more positives in the data set. At the extreme, if you classify everything as positive, your recall will be 1 because you found all the true positives, but your precision is going to decline, right? And so as you kind of add false positives, that will force your precision to decline. And these are both important to evaluating the accuracy of how we're doing. And so average precision is just the area under the precision recall curve. And usually this curve will be smooth in practice since precision and recall are between 0 and 1. And so it's going to give us average precision. Okay, so this is what mean average precision is measuring. And as I said, you want it to be pretty good in document applications because it can be costly to cut off the edge of a box when you have a number in there especially. Okay, so what's the problem with fast RCNN? So clearly fast RCNN is faster than the original region CNN, which is insanely slow. But you see that basically what's taking a lot of time here is running those non-neural methods to find like the blobby things that become your proposals. And that's really dominating, and it's still making fast RCNN be, in the grand scheme of things, fairly slow. Okay. And so the way to address this is an innovation called faster RCNN. And so faster RCNN integrates the region proposal network as a learnable part of the model following the convolutional backbone. And so the region proposal network uses a sliding window over the features map to get relevant anchor boxes, which are fixed size bounding boxes of varying sizes and aspect ratios that are placed throughout the image and represent approximate bounding box predictions. And then the region proposal network has a binary classification for whether the bounding box has an object, so it's background or foreground, and a regression head to refine the bounding boxes. It classifies whether or not the box has an object by looking at its intersection over union with the ground truth in that region. And so this is what faster RCNN looks like. So now we've added this region proposal network to it where we're kind of running this sliding window over the ComNet features map to get object proposals of different sizes and aspect ratios, and then we classify whether or not those contain an object, and we a change to their coordinates to refine them, and then we're going to put it again. After doing ROI pooling to get things a fixed size, we're going to have a classification loss. So what object does it contain? And another regression model to further refine the coordinates. And this provides significant computational savings because we're just using the same convolutional features map to do everything. And so this is an example of the anchors. So if the image is width by height, the features map will end up W over R times H over R, where R is the subsampling ratio. So for example, in VGG, that would be 16. So if we define one anchor per spatial position of the features map, the final image will have anchors separated by R pixels. Okay, so here's where the anchors are. And in order to choose the set of anchors, we define a set of sizes, so 64 pixels, 128 pixels, 256 pixels, and a set of aspect ratios between width and the height of boxes, and take all possible combinations of those. So faster RCNN paper has 9 anchor boxes. In practice, this is a hyperparameter and it needs to be set appropriately. And again, this might matter, so for example, if you have a column detection model, and you have a document with long, skinny columns, you're going to want to adjust the aspect ratios of your proposal regions to account for that, because you don't have many like long, skinny objects in, COCO, which is the data set that a lot of object detection focuses on as the benchmark, but you do sometimes get that in documents, so it's important to pay attention to these hyperparameters. And so this is the same image that we saw before. You can see that we have these boxes of different regions, and if an anchor extends off the image, we'll just drop it. Okay, and so the outputs of the region proposal network are 2K probabilities for object non-object, where K is your number of anchors, and from the regression head you get 4K predictions, which is the delta on the X and Y coordinates, width and height of the bounding box proposals. And these are applied to the anchors to get final proposals. And so for training, we take all the anchors and put them in 2 different categories based on whether they have significant overlap or minimum overlap with the ground truth boxes. And then we randomly sample those anchors to form a mini batch of size 256, maintaining a balanced ratio between background and foreground anchors. And we use all anchors from the mini batch to calculate the classification loss using cross entropy. And then we use only mini batch anchors classified as foreground to calculate the regression loss using foreground anchor and ground truth boxes. So since anchors overlap, proposals end up also overlapping over the same objects. So again, we're going to use NMS just as with RCNN. And after applying NMS, we keep the top M proposals sorted by score. And again, this is a hyperparameter that you need to choose, and this can be important because you want to have about 10 times more proposals than you have objects on average in your document. And I think in COCO, which is the main benchmark, there's something like an average of 3 objects in an image. They're natural images, whereas in documents you can have like hundreds and hundreds of objects on an image, different cells in your table or whatnot. And so you probably need to adjust this parameter. Okay, then the rest of the model is fast RCNN. And so we use the same ROI and RCNN layers that we saw with fast RCNN. So faster RCNN in short is fast RCNN with a region proposal integrated into the network. So in the original paper, faster RCNN was trained using a multi-step approach, but it has since been shown that joint training leads to better results. So there's 4 different losses, 2 for the region proposal networks and 2 for the RCNN. And we have the trainable layers in the region proposal network and RCNN. And we also have the backbone CNN, which we can fine tune or not. And so the 4 different losses are combined using a weighted sum into a multitask loss. And you can see that faster RCNN, like getting rid of that kind of non-neural region proposal part, really significantly speeds things up. All right, another thing I need to talk about, which was a major innovation in this literature, is features pyramids. And so features pyramids have a long history in computer vision, and there can be different types of features pyramids. First of all is an image pyramid, where you just have an image at different resolutions and features are computed on each of the image scales independently. And this is way too computationally costly with a CNN backbone, and it was mostly used in the pre-deep learning days. Alternatively, you could use just a single features map, and this was the norm for object detection before features pyramid networks. And the problem with just using a single features maps is that it makes it difficult to recognize objects of different scales, particularly small objects. And so, there's an entire literature on object detection with small objects. And if you're just using the image at a single scale, it can be difficult to recognize those small objects. And that can be a problem with documents, which can have some very small objects. Okay, pyramidal features hierarchy. So we reuse the pyramid features hierarchy from the ConvNet as if it were a featurized image pyramid. So we're getting this is like, these upper layers of the pyramid, these are not an image. They are coming out of the convolutional neural network. And so recall when we discussed convolutional neural networks that the initial layers extract the low-level features from the pixel inputs and assemble them into higher-level features as you progress through the network. And it's going to be a problem to detect objects from these low-level features maps, right? And so this is going to tend not to work so well either. Okay, so This leads us to a features pyramid network, which is what is used in practice, and it solves the problem of weak features at later layers for multi-scale detection. So it takes strong features and propagates them to the high-resolution features maps using lateral connections at each level of the pyramid. And so you can see now we have this features pyramid network where there's different resolutions, but we've connected them kind of at each layer of the COMNet. And so this is an example of a features pyramid network architecture. So recall vanilla faster RCNN, where we get this features map out of the CNN backbone that you see here on the left, and we have object proposals from that, and that's it. We're working at a single scale. Whereas when we are using faster RCNN with a features pyramid network, then we have outputs from the CNN that are at multiple scales. So this is going to make it easier to detect images at multiple resolutions. Okay, so that's features pyramid network, which in practice is an important part. And it's just, again, very useful to have these different resolutions from the features pyramid network because we have to detect objects of very different scales. Okay, I want to say a final word about object segmentation. So this is, instead of just recognizing the bounding boxes, you segment the objects that are in those bounding boxes. And again, you know, with documents, oftentimes that's not really necessary, but the successor to faster RCNN, mask RCNN, essentially just adds a fully connected branch to faster RCNN to predict masks. And so it's a semantic segmentation problem inside each region proposal. And the mask loss is computed by taking the cross-entropy loss between the predicted mask and the ground truth for each pixels. And it also incorporated features pyramid networks. ROI pooling is modified slightly using a method called ROI align, which allows for the finer spatial localization required to predict masks. And this is trained on Microsoft Cocoa, like most stuff in this literature. And so this is just mask RCNN, so you have your image and you pass it through. In this case, it's showing a ResNet, and you get your region proposals, and then you do both, you know, your classification where you predict boxes in their classes, and then you have the mask head, which is predicting the masks. And you know, it's showing in the paper that even if you're just interested in only the boxes and their classes, that you get better results using mask RCNN, because you have this additional loss and the model's being trained end to end. So by virtue of having the mask head providing this additional supervision, you can do better. You know, in my experience, kind of with documents, those gains are extremely marginal. So using faster RCNN versus using mask RCNN, you know, in a case where you have documents and you just want to get out the bounding boxes in their classes, like say this is a newspaper headline or caption or etc., I don't think it makes much of a difference. Okay, the final framework I need to mention is YOLO, which stands for You Only Look Once, and it treats object detection as a regression problem. And so we divide the input images into a 7x7 grid, base bounding boxes within each grid, and for each of these predict offset and classification scores. And so essentially it's analogous to just using the region proposal network, except with all C classes plus the background, rather than using the region proposal network, which is background, non-background, and initial bounding box predictions, and then further refining this with specific classes and additional bounding box refinement. And so it's intuitive that like something like faster RCNN is going to be more accurate because it has this two-stage approach, whereas YOLO, you only look once. You're not doing those multiple refinements, and so accuracy tends not to be as high. I think like with older versions of YOLO, we found the difference could be like quite significant, but with the more recent versions of YOLO, it seems like the differences are more marginal. And so if you have a context where you're solving a large-scale problem and you really care about computational efficiency, I think YOLO is very much worth considering. All right, so I want to say a word about object detection with transformers. And so transformers for object detection actually predate VIT, and so there is a model called Dieter that uses a transformer architecture to model object detection as a set prediction problem and achieves near state-of-the-art results. However, Dieter made use of a CNN backbone, much like MASC or faster RCNN, and therefore was not a fully transformer-based approach to features extraction in images. And so in some sense, Dieter can be thought of as using the transformers to replace everything except for the CNN backbone for object detection. Now, however, there's a high-performing object detection model that entirely uses transformers for features extraction for object detection, which is Swin. And there's also other transformers that you can use for object detection, and we'll see a little bit of this next lecture, but Swin is definitely the most prominent one that you'll see people using. Okay, so Dieter was everything but the backbone for object detection, whereas the Swin transformer is the backbone for object detection. So Swin is a hierarchical transformer whose representation is computed with shifted windows, hence Swin. So Swin aims to solve the problem of generating multi-scale features from high-resolution images using transformers, which is a key component of doing good object detection that has no clear analog in the original transformers architecture. And so we've talked about this a little bit earlier in the class about how ConvNets actually have useful inductive biases for solving computer vision problems, and transformers don't have that. I mean, the architecture originally came from working with text. So this kind of shifted window approach, which is very reminiscent of convolutions, is actually kind of useful for being able to extract multi-scale features from high-resolution images, which is key to object detection. It's particularly key in documents because documents, they really need to be quite high resolution, especially if you have a lot of text in them. So Swin-T also aims to address the vision transformer's seeming incompatibility with doing dense prediction, which is what you need for semantic segmentation, where you're predicting at the pixel level, because of the computational complexity involved in self-attention at the pixel or near pixel level. VIT doesn't, really allow you to do dense prediction because you're working at the patch level. Okay, so let's talk now a little bit more about the Swin-T architecture, which again, to summarize, is going to take some of the inductive biases from convolutions that are actually very useful for image processing and for object detection in particular, and it's going to apply those to the transformer. So Swin-T creates a hierarchical multi-scale representation of an image analogous to the features pyramid that we just saw by first performing self-attention on small patches of an image only within local windows of the image. It then merges neighboring patches and performs windowed self-attention on these new larger patches, and it continues this pattern throughout the depth of the transformer layers. And so you see a conventional kind of VIT on the left, whereas on the right, you see the attention of Swin. And so it's starting out by having kind of at a very fine level, having attention, but only within these patches. And then at each stage, it aggregates them up. And so you can see how this is in many ways kind of reminiscent of what a convolutional neural network is, where as you kind of go up through the features pyramid, you're getting essentially, with this shifted window approach, you're kind of pooling features across the image and allowing there to be a broader receptive field. So this in some ways looks a lot like a convolutional neural network, but it's entirely transformers. And so each stage of Swin-T is composed of multiple transformer blocks, and it produces something akin to a features map, which can be used as an input to create a features pyramid network and as a backbone for something like MASC RCNN. And so for Swin, the number of patches in each window is fixed, and thus the complexity becomes linear to image size. And so this is just showing you the Swin architecture. And so you see you're going to have kind of multiple layers of the transformer where you're applying this at each step. So the authors of Swin show that one of its most important design choices is to perform windowed self-attention over windows that shift in spatial extent across alternating layers. And so they say the shifted window partitioning approach introduces connections between neighboring non-overlapping windows in the previous layer and is found to be effective in image classification, object detection, and semantic segmentation, increasing the model's downstream performance on all of these tasks. And so shifted windows as opposed to sliding windows are lower latency on real-world hardware in the context of transformers. And so that's why they're kind of using these shifted windows as compared to sliding windows, because all query patches within a window share the same key patches. All right. And so this is showing graphically what these shifted windows look like. And so you get cross attention in layer 1 within these blocks, and then you shift them for the next layer. So what are the key takeaways from Swin? Essentially, by applying transformer self-attention at multiple scales, Swin is able to computationally efficiently extract rich features from even high-resolution images. And different from image classification, ImageNet is not that high resolution. Whereas a lot of stuff you do with object detection, you may need much higher resolution images. And so VIT still, it really doesn't work great. It's fine for images of the resolution of kind of 256, I think, by 256, what you get for ImageNet, but doesn't work so great with higher resolution images. Swin, by virtue of having this shifted window attention, works very well with large images, which are sort of a mainstay of object detection, state of the art on COGO. I'll say it was very straightforward to implement Swin. We found that it doesn't really differ from ConvNext or using a ResNet. And again, of course, your mileage may vary. But I don't think this is a transformational advance over just say using ConvNext, which will have a lighter memory footprint, at least if you use ConvNext Tiny. Okay, so that's Swin. And so I think the punchline is you can use transformers for object detection. They work well, but they may work similarly to just using a ConvNext. I've focused in these lectures on kind of the faster RCNN series. There's something called Cascade RCNN, and I'm not going to go into it here, but you might hear that mentioned. And it can be very marginally better. I'd say in our experience, it looks pretty similar to faster or mask RCNN, but maybe marginally better. So using Cascade RCNN is a reasonable thing to do too. You can use either one, and it's also like a two-stage architecture faster RCNN, and I think it's going to give you broadly similar results. Whereas YOLO, you're going to take probably a little bit of an accuracy hit. Maybe more than a little bit of a hit. You have to look at it. Your mileage may vary, but it's cheaper to run YOLO, and you might care about that if you're scaling something up. And so kind of summary, I think, faster RCNN/mass RCNN are a very reasonable place to start. You can see if you can squeeze a little bit more accuracy out with Cascade RCNN, although I think it's similar. And if faster RCNN is just still too slow for your application, you can consider using YOLO. All right, and so that's kind of introduction to the theoretical side of this literature. So now I am going to kind of make a second video where I talk about the practical side of this. I always kind of like to divide the lecture videos up when the lecture is going to last a while, because the software that Harvard uses to record these to Canvas is kind of buggy, and I'm always afraid it's going to crash at the end of the lecture. So I'm going to stop this video now, and we're going to have a second video that's more about the practical side of object detection. So please make sure to watch that video as well before lecture on Thursday. Thank you.